Okay, looks like it's time to begin. This is my first time doing a remote lecture. First of all, can everyone hear me? If you can't, send me a message, let me know. See if I can do adjustments. So it's amazing how things have changed in a week. Last week they announced we were going to, let's see, taught classes in 3 weeks, and now they're saying they don't want people on campus at all. And just, they're locking all buildings down, and you have to have special permission to go to campus. Hope everyone's doing all right. So let's get started where we left off. Well, first of all, let's talk about the current assignment. People seem to be having trouble. So I think what we'll do is we will change the due date until March 24th, which is next Tuesday. Give more people time to deal with the issues. That said, I will start where we left off last time. So let's, okay, so we had someone had raised her hand before I click on it. Things disappeared. Still getting used to all the features here.
A little of this work done before the weekend, so you feel.
I agree.
Dude, I want to get it.
I take it back. There's audio.
You don't have to go home. We can just buy some here, man.
So can everyone hear me?
Yes, I can hear you.
Yes.
Okay, so I'm going to, we'll see how it goes. If it's too much background noise, I'll mute everyone. Yeah, I think I'll mute people so they can. So if you have a question, you should be able to unmute yourself and then ask the question. So last time we finished, we were talking about using Spark. And so I'm going to take off where we left off, looking at doing regression on Spark. So we have a model here where basically it's just a linear function, right? So it's just f of x equals x. Is everyone seeing the my PowerPoint slide? No, if you're not, we'll. Now, the one complication is that if we're doing machine learning models on Spark, They assume the SVM file formats, which is slightly different. And basically, it's, the full format is we've got our dependent variable, and then we have all our independent variables with a label and then a value separated by this column. And we continue on. So in our example, here's what our file will look like when we transform it. Here is, f of x, and here are our features, and this is the first independent variable. And so we need to be able to convert usually a CSV file into this format. And the basic process is, we need to read the training data, create a linear regression object, fit the linear regression model object to that training data to get our model. And now we can read the data we want to test on and evaluate that data using the linear regression model. Not that much different than what we were doing before with straight pandas. Once we have the data in SMD format, reading it is pretty straightforward, right? It's just, Spark read which format we're reading and which file we want to read. And then we can look at it. And indeed, we're getting independent variables here, independent variables here, and independent variables here. And here's the file that we were reading. It's already in the format. Right, so once we have the file in the format, it's pretty straightforward, as in pandas, right? And the pandas, we can just, it's pretty straightforward. Read the training data, set how many times we want to iterate through, and then we can fit our training model. And since the linear regression model, we can look at the output by looking at its coefficients. And it's pretty close, right? Because we're looking at, it says the x coefficient is basically 1, and that intercept is pretty close to 0. Then we can look at the R2 value, right? And the R2 value is basically 1, which means it's a perfect match. We can look at the residuals, right? And residuals, bounce around a bit, but they're not too bad. Now, what all remains us to do is to actually look at some actual data and use our model to fit it. And let's see, so here we are reading the data. Given that we already have the model, we can now evaluate on the data. And We can then look at our predictions. Right, and it's saying here, okay, for an input of say -50 is predicting -49, input of -10, predicting basically 10, and look at 50, it's just a little bit off, right? Just a tiny hair off, right? And that's essentially noise. Right, so as you would hope, if we have a such a clean model, it should match pretty good. Any questions, issues so far? No comments. No. This is all new to us. As time goes on, we'll figure out how to do this better and better. Once we've built a model, we can use that later. But first we have to save it, right? And just save it. And then of course, so here's our entire program. And if we can save the model, then we need to be able to read it again, right? So here is, reading that model back in. And now we can use that same model to match other data. And this is pretty much the same process we'll use for most other machine learning models on Spark. Now, most of the data you're going to get is not in SMB format. More commonly, it's in CVS. And there are a couple of things we can do. There's some transformers, RFormula and vector assembler. So again, let's look at this file and see how we can convert that to the SMV format. Vector assembler, the process is pretty straightforward. You create the vector assembler, you set the input columns, set all the columns, and then you transform the data frame. So here is just reading the data, standard Spark read format. And we get a Spark data frame. And if we can look at the input, our independent variable is labeled X. And so here, our input column is, again, just X. And then we want the output column. It's pretty common to call it features. And then we can just call transform on our Spark data frame. And, here's the result, right? We get, here's our independent variables, our X, and our features. Now, one of the problems with using Python is we never explicitly write down the data type we're dealing with, which at times is nice, but other times it's a little frustrating because, what is this exactly? And there's our input file. Here's another example. I'm adding some random noise just to make it slightly more interesting. And there's two independent variables, X and Z. For the process now converting this to SMV format is basically identical. Again, remember, when we read a file in Spark, we can specify the schema of the file we're reading, or we can let Spark try and guess it. Sometimes guessing doesn't get it right, so here is just specifying the schema. And once we've done that, the only thing different is our input columns includes both independent variables. Pretty simple. And then here is, right, again, creating a model, and our coefficients are almost 1, and the noise is a bit more, so it's definitely not getting 2 anywhere. Okay, so what we need now is, I think we need to do an experiment. And we need to figure out how you can ask a question. So let me, Garrett's always a good one. So Garrett,
Yes.
can you raise your hand? Oh, okay, Brianna, Brianna raised a hand.
I don't know how to raise my hand in here. I have a thumbs up and a clap.
Yes, I have.
I could let you know.
Yes.
So if you go down on the bottom next to participants and you click on participants, you're gonna get like a new window to pop up. And it has the options lower hand or raise hand, yes, no, go slower, go faster. And it'll just pop up on your end as a notification.
Okay.
That was super helpful. Thank you.
You're welcome.
Yes. Everyone get that? Okay, so a bunch of people are saying yes. Good. Anyone not get it? If you didn't get it, say no.
Hey, Professor.
Yes.
Do you think you're gonna change your office hours after your first experience today, or?
I hadn't thought about it. Why do you ask?
Got it. Okay.
And I did think initially, well, I have thought about moving to a different day Because then you'd be able to contact me, Tuesday, Thursday, you're doing lectures, and then say Monday and Wednesday other times. But I decided not to change things too much and see how it goes as we go forward. I think we're all just
Able to go a while ago.
What's that?
I was not able to go a while ago, so I was wondering if you had like a different day that we could do it, or yeah, just, or if you were planning to separate your classes, office hours and stuff like that. So yeah, just let us know if you plan to change that.
Yeah, from my end, the office hours went pretty good today. I did change them to 2 to 4 instead of 3:15 to 5:15, in part because when I go to school, I get to move around. In my lecture, I'm standing up and I can move around, but now I'm sitting in my desk, and I'll be sitting, for 2 hours from office hours, and then another almost 3 hours for classes, and I can't sit that long, so I wanted a break between my office hours and my class.
Yeah, I totally understand.
Okay.
Yep, thank you.
So that was how we can transform CVS file using a vector assembly. There's another way of doing it, which comes from R. So those of you who know R will be familiar with this. So basically, there was this little language they use to describe the model. And so we're basically saying, right, this tilde basically says, look, y depends upon x and z. And you're basically saying that, y is equal to some constant plus, b times x times c times z. And once we do that, right, then we can, that minus 0 is going to subtract off any constant value. And then we can start looking at, if two variables interact with each other, we can get another term, right? So we can use this little language to create our model or describe our model. And then we can actually create an R formula, but specifying what the model is. And once we've done that, it's pretty much the same to fit the data, and then we can transform the data to get our data frame in the right format. So data frame starts looking like this. And so we've got our features column and our labels. And that's pretty common too, to use label as the dependent variable. And here's our input file. All right, so now we can actually use that transform data frame in our regression model. In another example, we've got two independent variables. Here's our file we read in, and the output from our, after we transformed the file using the R formula. So it's not, I don't know if different ones are more efficient or not. I think it just depends upon what you're more comfortable with. People coming from R are probably much more comfortable using the R formula. Some terminology, computer science, we really like to have, fancy terms, hyperparameters, sounds fancy, but they're just parameters we set before we start the learning process. Things that we can't learn from the data. So in regression, things like the, feature column, label column, how many iterations you want to do before you stop. How much weight you want to give each column. Various things like that, which we're not going to be able to guess from looking at the data. And then, there's typical Python. Here's all the parameters we can set for linear regression. Quite a few of them. And this elastic net parameter, that's really fun. It specifies some properties, how we want to fit the data. And so there's, various values, different algorithms to use to try and deal with the coefficients. What happens when you get lots of coefficients that are close to zero? Is that because they really are close to zero but not zero, or just because there's computational error? So L1 will tend to shrink a lot of the coefficients to zero. So we get a lot of coefficients, or if coefficients are not zero. And I don't know which ones are better. I suspect that since we have options, it's going to depend upon on the data and what we're doing with it. And this is, again, what happens these days with machine learning. Most of these algorithms are well established, but we have to, what the machine learning people need to do is understand what implication choosing different hyperparameters means. And I've known people who, graduate students running various machine learning models that do it for weeks on end, just tweaking all these hyperparameters to see what works best on their particular problem. Right, and so we can actually, partition your data set into 3 parts. One is to train hyperparameters, see what works best, then train the model, and then test our model. But so the fun part, we create a grid, but that all of a sudden becomes, can consume a lot of CPU cycles going through that grid, searching the parameters. And overfitting is always a problem. And here's an example we've seen before. It's like, here are the data points. right? And the data looks fairly linear except for a couple outliers. And if we, and you may remember from algebra classes, given enough degrees, we can actually create a function, which we do here, right, that meets all the points exactly. And so we get some crazy function, right, that matches the data completely, exactly, but I don't think this endpoint here, right, where it goes way down is a proper fit. So one has to be careful. If we tweak enough knobs, we can make data fit our particular data set very well, but it may not fit the underlying operation that's being done. So linear regression is perhaps the easiest machine learning model to talk about because it's so simple and we can draw lines, particularly when you got two-dimensional data. But there's a lot of different types of regression we can do, which uses different distributions, and some of them can be used for discrete values. And this leads us to general linear models. The categorical variable is one that takes on fixed values. It could be the sex, it could be what city you live in, the state you live in. And if we've got categorical variables, you're not going to be able to do straight linear regression on it because it's not continuous in a sense. So logistic regression or legit regression is one where we can model it with dependent variable being categorical. So typical examples, given certain tests, can you predict whether someone has a disease or not? How often will vote? So here is, some fake data I created to illustrate how to use the model. Basically, how do we how can we predict that people are going to pass an exam based upon how many hours they studied? I mean, it's completely made up data, but should be good enough. So our hyperparameters run our, is it multinomial or binary? How do we mix L1 and 2 regularization? Whether or not we should try and look for intercepts. On the iterations we want to do, there's a bunch of various different parameters we can set. So let's look at example. So here we have, again, I'm specifying the schema. Make sure that file is read properly. Using RFormula, saying the past depends upon hours. Two-step process to take our data frame we read from the CDS file into the CDS format using RFormula. Once we've done that, I split the data into two parts, one for testing, one for training. And I specify how much I want for each. So I'm using 70% of the data to train and 30% to test. And then we can look at each set. So just iterate in dividing the data set into pieces. And we want to do it randomly so we don't introduce bias in any way. We've already seen how to deal with creating the regression model. Here we just need to look at logistic regression, and then we can train the model. And now we've got the model. And then to put it all in one line, we're evaluating the model in our test data, looking for predictions, and then show them. And we get, various, so first of all, here's the actual test data, the raw prediction numbers, and then we can look at the probability that they're looking at. Right, so there's a 98% probability that this is 0. And so even though the predictions are binary, either 0 or 1, you can see how close, how much we should trust these values. Clearly this one is much more confident of it than we are with the latter one. The latter one was basically 0.3, which is pretty close. But when you get 0.09 or 0.002, those are much, much more accurate predictions. Now, one of the interesting things is talking to people is much different than talking to a machine. And I've read studies where people who've got repetitive stress issues with their hands start using voice recognition to actually type things on the machine. And after a while, they find that their voice becomes hoarse because they don't talk normally. It's going to take me some time to slow down when I talk and talk normally. I start to feel, oh, I'm talking too fast and my voice is starting to get a little sore. Yeah, but we've seen a logistic function before. And we're using this to figure out how to map these raw values up into probability of being either 0 or 1. And if you study machine learning, you're going to come across the logistic function a lot because it's, for one, it's used very, very commonly in neural networks. And that's a function. Now what happens is that when looking at processing data like you do in assignment 2, there's this whole number of steps you take, right? You have to read the data, you have to transform the data into the right format, then you have to clean the data up, and you have to add features, remove features, remove rows which don't have data in various columns. And then we maybe a bunch of transformations we have to do. And then we may need to create models and then look and see how the models perform. And so Spark allows us to create pipelines. We can combine them into a pipeline of, okay, we're going to take the data, we're going to transform it in these various ways, and then we're going to apply the various models and look at how the models perform, and then we can then apply that pipeline to different input values without having to specify the whole thing over and over again. Here's a simple example of creating a pipeline. So, my RFormula to convert the data into CVM format, and then computing logistic regression on it. And then our pipeline is, well, first we are going to apply the RFormula, convert to the right format, and transform that data or pass it on to regression, and that's our pipeline. If you've done any functional programming, this is a very common process where you set up a chain of functions to act on some data, and the output of the first part is sent to the input to the next function. Basically what we're doing here. So again, all we're doing is I'm reading the same data. I'm getting the test and the training data. And then I can apply my pipeline to train the data to get our model. And then I can use that model to look at the test data and transform it and show the output. Any questions so far? Okay, no one's raised a hand. So I'll move on.
Professor, I think there's a question in the chat.
Okay. I'm looking.
I can read it aloud if it's too hard to find. It just says, since the homework due date is now March 14th, will the exam still be on March 24th? How will it work logistically?
So the question is, since I've changed the due date to March next Tuesday, my current thinking is I will then give the exam over spring break. And I'm looking for, all right, so why do I not see the chat? Oh, there's the chat. Okay. There. Too many places to look. Okay, well. Very interesting. Well, I don't see that particular question in my chat. Well, doing this remotely is going to be interesting as we go forward. So in Spark, we've got a number of transformers. Some we've seen with a vector assembler. There's quite a few. The number dealing with text, which is always exciting because dealing with English, there's always various complications that arise in terms of different spellings, misspellings, etc. And a number of different selectors. One thing you have to worry about is what happens when we've got data, we've got extreme outliers. And so we can scale the data in a number of different ways. So the standard scaler will transform it so the standard has unit standard deviation, and the mean would be 0. Right, so looking at these values, we have this value is extreme, whereas it's -1 or 0.1, 1.1, and 10.1. And so if we do a lot of different algorithms will give us far more weight than it probably deserves. Using the standard scaler, maps it down. The 0.1 gets goes down to 0.01, and that 10 gets mapped down to 1.8. So these outliers don't carry as much weight when we transform it this way. You know, another way of scaling it is just to specify a min and max. You know, it does reduce the impact of these outliers. The problem is that the small value is 0.91 gets mapped basically 0 because it's just too small compared to the maximum value. And again, which one we deal with depends upon what data we're talking about. So here is an example, right, where I'm again just creating a data frame using those values. The dense refers to a vector can be either dense or sparse. And that the difference there is if you've got data which is very sparse, often most values are 0 or non-existent. What do we do? You know, if you've got 1 million values or a vector 1 million long and only 1,000 of those values are actually there, you don't want to create a vector which contains 1 million values. So we're going to do a different structure to store the value. Dense meaning, well, it's basically your standard array type of situation where we're going to have a slot for every value. And you know, again, features is pretty much a convention using my max min scalar, and you know, fitting the data. And again, I fit the data and then I transform the data, and you know, then I can look at the output which we saw earlier. And there it is, right? You know, more exciting stuff, right? Just another way of transforming, scaling data, specifying a range, and then in this case, I'm specifying a range from -1 to 1. And so the smallest value goes to 1, -1, the largest value goes to 1. Let's see if I put everyone to sleep yet. You know, binning the data. You know, the data may have a range. If the range is, you know, floats, and we want to see some trend, we may need to actually put them in bins or buckets. So we can look at how many values in each bucket. And that's what the well-named bucketizer does. Again, example, here's my values. I'm going to try and put into buckets, create my data frame. And then I'm splitting my buckets to go from -infinity, right, to 0.5, and then 1.4, and then 1.4 to infinity. And then I can transform the data, and when I've done that, now here is which buckets they go in, right? And you can see that NaN has been put in the last bucket, so it's been treated as infinity. Another way of binning data is just if you have binary data, specify at what point should it go in the first bucket and which point should go in the second bucket. So here I've just picked 0.05 to be the splitting point. And then you can see that 0.1 goes in the first bucket, 0.8 goes in the second bucket. And then here we can specify how many buckets we want, and then it's going to take the entire data set right, and convert it into 3 buckets. And here what we're doing is I've got a categorical column which contains strings, which can be hard to compare to each other. And so I can use a string indexer to convert that into, again, it's still categorical, but instead of being strings, it becomes integers. But note that it's an algorithm, so it's picking values which humans would not do. We would put A in 0, we would B in 2. But these are really categories, right? There's no relative position. It's just, you vote for Republican, you vote for Democrat, you vote for Independent, right? So there's no logical way of saying, look, Independent should go in between Republicans and Democrats. So just make sure that, all the C's go to the same bucket. And that is a good question. And we can specify 3 different ways to throw an exception. We're going to skip rows that contain the unseen data. All right, we're going to put them in their own bucket. Yet another encoder. I think I will skip over this. And finally, we get to not the complete SQL in Spark, but as we'll see later, we can actually do a lot of transformations using SQL. So I have this SQL transformer where I can start using SQL to transform data. So here, again, I'm creating, a very simple data frame. Has 3 columns, ID, V1, V2. And I just give 2 rows. And my select statement is, well, what I'm doing is I'm going to add those 2 columns and create a 3rd column called V3, and then I multiply them together to get V4. And then I'm showing it, which should be, all right, so here's my input values, and now we're getting, it did what we said. But the thing to note here is it looks almost like SQL, but suppose our select but then we have this from underscore underscore this underscore underscore. So it's not quite SQL as you might do it in Postgres or Oracle, but it's close. And that then lies in the problem is if it's close, where does it differ? And notice again, this is a string, so there is no, well, it's like Python, right? In Python, there's no compilation phase, and so you don't know that you mistype something until you actually run it. And the same thing here, if you mistype a SQL statement correctly, you won't know until you get a runtime error. So there's a bunch of models we can choose. Looked at logistic regression. There are limits to what we can do. So we can have up to 10 million features, which seems outrageous. And we can basically have as much training data as we want. And alpha classes, less than 10 million. Decision trees, which we'll look at a little bit later. We're limited to 1,000 features, in part because the algorithm is slightly more complicated, so it takes longer. Efficiently random forest, which basically is a set of decision trees, holds more. Even though we're dealing with Spark, there's definitely limits. It's hard to imagine people having 10 million features. Well, I think I'm going to end early. First, let's see, are there any questions, issues? I will send out a notice to the class letting know that the deadline for assignment 2 has changed. I have had some interaction on the wiki and through emails from students with some issues on assignment 2, which I'm working on.
I had a question.
Yeah.
Yeah. So I think someone asked on the wiki if using VAX and DAS, should we be using different source files? Because I was trying to read in the HDF using DAS and it was complaining about some key value that I'm supposed to be using, some parameter.
Yeah. I haven't had time to test this, but students are reporting that if I create a HDF file in one system, I can't read it in the other system.
Right. Yeah.
So you may have to create separate, for each system, create a HDF file in that system to use in that system.
Okay, and are you expecting it to be like in the homework it said one big HDF file, or should it be like filtering through several HDF files? Does it matter, or
When you say filtering through,
or like for looping through to read it when it's getting the data? Because I think in DAS you can filter through several HDF files at once, like a list of files. Do you prefer it that way, or just one big HDF file?
well, initially I was thinking of one big file.
Okay, just checking.
Any other questions?
I have a question.
Yeah.
So for task 3, and we're trying to make the heat map against the pickup locations,
Yes.
I'm not quite understanding how our map is supposed to like know where these pickup locations are. I'm unsure like what you mean just by plotting the pickup location against the average fare amount based on like a heat map, because like I was looking over the article Jupyter Notebooks and they have like a whole grid system set up for the pickup locations and drop-off locations. So I was just wondering how you wanted us to do that task only using the pickup location.
If I remember correctly, they also had a heat map for looking at the number of people too. What did I say in the assignment? Oh, but yeah, so number 3, yeah, so I'm expecting that yeah, you're going to use latitude and longitude, right, of where they were picked up. And then color code the heat map by the average fare amount from that particular point, pickup point.
Okay, so then that, do you just want us to trash the other, the rows that don't have the latitude and longitude for that specific task? Because there's a bunch of the CSV files that don't have the latitude and longitude and only have the pickup location like value.
Yeah, this, and this is a standard problem, right? What happens when the data is not in the same format? It is possible to use those zone pickups to find guess or compute relative longitude. But that's not going to be very accurate because I assume zones are relatively large. Plus it adds more work. So yeah, just if you don't have latitude and longitude, then don't use those rows.
Perfect. Thank you.
Let's see. Ramesh, do you have a question?
Yes, Professor. For the CSV files that have like the location ID, so what you're saying is we do not have to look into the shape file to probably get the latitude and longitude and just ignore those rows
That is
because
correct.
okay, because the shape files has an attribute called the geometry, and the geometry of all the burrows are not uniform. Some of them are on the polygon format and some of them are on the multi-polygon format. So like extracting the latitude and longitude is becoming quite tricky there.
Yeah, and plus, I mean, several things. One is it's not clear how accurate it would be. It's not clear how big these shapes are.
Mm-hmm.
And your goal assignment is to look at the relative performance of doing some of these computations.
Okay.
So going to extra work doesn't provide us any extra data, useful data. So just if there's no latitude and longitude, don't use those rows.
Okay. Thank you so much. Yeah.
Any other questions, issues?
Yeah, I'm having an issue. I don't know if anyone else is having this, but I am having a hard time just creating a giant HDF file from all the spreadsheet files. Did anyone else have that problem, or am I the only one having a hard time with that?
When you say you have a problem, what sort of problem are you having?
Well, I'm trying to follow the example code that was provided on the article, the Bo article, and in that example, they load all the spreadsheets into a pandas data frame, and then they export that into a Bo data frame, and from that create a HDF file. And when I attempt to do that, my kernel quits because I think it's just too much data for a single data frame to have all that. So I don't know if there's any other ways to do it that I'm not aware of.
But this is one of the issues that a student contacted me with earlier today, and I haven't had time to look into it. I hope to go through it tonight or tomorrow, and I'll get back to you on that.
Okay, thank you.
Any other questions, issues?
Professor, my only other thing is, so just to confirm, the homework is moved to next Tuesday due date, and then we're looking at potentially moving the exam to spring break time.
Correct.
Awesome. Thank you.
Okay. Well, I hope the first remote lecture wasn't too boring for you.
Hello?
Yeah.
I have a question regarding the homework.
Okay.
So You said for question 3 and question 4, where we need to produce a heat map and calculate the arc distance, we only need to care about the CSVs that have the longitude and latitude, right?
That is correct.
So, but for the question 1 and question 2, do we need to do these problems using all of the CSV files?
You don't have to.
I don't have to. Because what I did for creating the HDF5 file is that I actually find the intersection of all of the CSV files, because apparently to solve these 4 problems, we only need to have a certain number of columns, right? We don't need all of the data.
That is correct. You don't need all the data.
Okay. Yeah, just checking. Okay, thank you.
Well, I'm going to sign off now so I can take a short break before my next class starts. And we'll meet again on Thursday.
Thank you.